Type your registration numbers. Okay, so today we are going to see this multi-layer artificial neural network backpropagation algorithm in brief, and then we will see the factors affecting training of this network. So in last class we have seen this diagram where we start with initialization of all the connections, so randomly, and then we calculate the output by passing on this input from training data set. So there are two basically data sets in neural network or in machine learning, which is training set and test set, test data set. So sometimes people also use validation data set. So in Keras, it can be done very easily. We can partition data randomly into such sets. So if this is the big set, big data set, then we can divide maybe some around 90 or 80% of data for training purpose, remaining test for testing purpose. So this is training, and this you can further divide maybe some 60 here, and say this will be 20 then. This is called as validation. So what is validation? So we will train the network using these samples. Within that we will, within this training set itself or training phase itself, up to this from here to here, we are going to use these samples to validate what we have done or what we have understood or what the network has learned. Then we may adjust the parameters here, and then we go for a retraining. Okay, so this process continues till the desired goal or the parameter used for checking the accuracy, maybe error of this network is satisfied. Till that time we may iterate. Once this iteration is over, then we present this reserved set which was not shown to the network while training. Okay, so this is a fresh copy, or you can say a portion of data set kept intentionally separate. Then we test on this, and then we report training error or training accuracy or test error. Okay, so that is done normally. So here we are defining some error like this, d minus o square. So this is the parameter which controls the iteration, how many times I will iterate. So it depends on this error. And here we normally calculate this delta signals or error signals which are used to change weight here. Okay, so adjust weight of hidden layers, adjust weight of output layer, and iterate. So this is iteration logic. Now that was the broad idea. Now how do I select before I say train something? How do I design the architecture of that network itself? There are many parameters that affect the training, then in what situation I should do what. So that we will see briefly here. Say the list of factors affecting the convergence of backpropagation. So convergence of backpropagation means you achieve the target value of error or some signal parameter that you are using to control the backpropagation. So here it was the error half into d minus o square, that is summation over say output layer, that is I equal to 1 to say capital K, say K number of classes. Now the factors that affect are enlisted here. The first and important one is initialization of weights. How do I do it? Then the type of learning or type of training. So you have basically three options. First one is incremental learning training, then batch training, and third one is the hybrid approach of these two. It is called as mini batch. Okay, then the third important parameter is activation function. What is the role of activation function? How it will affect the training. Then next one is steepness of the activation function, the slope of that activation function. The fifth one is learning constant. So you know that we always write change in weight is equal to some c into d minus o into f dash into x, something like this. So this c is a constant called as learning constant. So you may find different symbols here, sometimes like this. In different books, they use different symbols, so we can stick to any one of them. So that doesn't matter. Then the final one is network architecture. Overall architecture, how you select it. Now let us see these parameters one by one in detail. So factors affecting convergence of backpropagation. The factor number one is the initial weight. So initialization strongly affect the final solution. Okay. Initialization of these weights strongly affect the final solution. Network shall be trained with small random values. So you should initialize the network with very small random values. Same weights for all connection may not train network properly. Somebody may say, okay, I will take say 0.1 everywhere. All weights or all weight matrices I will assume equal to 0.1 for each entry. So this is not a good idea. Assume everything same value. That may not train your network. So you should avoid such kind of things. Empirically, it is observed that continuing training after certain minima of error results into undesirable drift of weights, and error keeps on increasing. So what happens sometimes, suppose I draw say like this. So this is some error and these are some number of iterations. You may observe that error is falling down. Okay, for some time it is here, it reaches minimum and again it's coming up. Okay, So if you observe such a situation in your network, best solution is randomly again reinitialize your network. So that is a practical solution. If you find such kind of a drift of weights and error is increasing, then you should note that your initialization, or rather random initialization of weights, was not good, and you should do or reinitialize the weights. So what happens is, suppose I take some 1D kind of a thing. Say this is some error surface, and on x-axis we control weight, and here is some error. Suppose by chance your assumption is here. Okay, your assumption is here. That means you have assumed some weight which is located here. The corresponding error is here. When you do negative gradient of error, so your weights will be adjusted from this position maybe to this position. So your error is reducing. Then maybe you are here at, say, third, you can say, cycle. Now this is, say, minima. Okay, you land to this minima, and when you go further you may not come out of this value. Okay, your global minima may be, suppose I draw like this, your global minima is somewhere here. That means for a given problem this is global minima. Okay, so you want to reach to this possible point, but when you see, when you land to such kind of a point where derivative is 0, it is not a minima, global minima, it is called as local minima. So since here the gradient is 0, your algorithm will see that I have reached the minimum point and it will terminate. Okay, so but see, you have done something and you start training again with the, by changing, say, learning constant or so, you may travel like this. So during this period your error is again increasing. Okay, such kind of things happen practically, and whatever I have drawn is some random surface, and maybe there are many complicated surface, error surface actually appearing in real problems. So you can see error was falling down and it is creeping again, increasing again when I iterate more. So such kind of thing happens. So best idea is to randomly reinitialize weights. Now by chance, suppose when you do reinitialization and you start your journey from this point, okay, so next random initialization is here, then you will see that you can travel in this direction and you can reach this minima. So whenever such thing happens, that error was going down and then you are again moving up, then you reinitialize your weights. Now when you take the training data, or the data set which is, say, available to you, you can do, say, in broad sense, two types of learning. First is incremental, and the second one is batch. Now what is incremental, what is batch? So basic difference, in incremental training, weight updation is done after presenting each pattern. Okay, once pattern is presented, error is calculated at the end of the network at the output side. So there is some error, then it is used, deltas are calculated, and weights are updated immediately. Okay, so that is called as incremental running. So input is applied to the network, output is calculated. So this is input, output is compared with desired response. So D minus O is calculated, it is squared, and then whatever error signal is generated, immediately change in weight will happen. So when I present x1, this will happen. When I present x2, this will happen. For each pattern you apply one by one, this change in weight will happen. Now what happens during such kind of training? Training may get, say, skewed towards the last train pattern. Okay, so last training pattern or the latest pattern may skew your training. Say it will pull that weight towards that particular error direction to larger extent. So that will be the dominant direction, and that may create sometimes a problem. So solution to that was to remove this skewness. The solution is change the weight after a batch of training samples. So what we do, say this is my training set. I apply first pattern, suppose this was x1, and then due to x1 there is some change in weight. Okay, maybe say w delta w1, that is calculated, but actual weights are not changed. Okay, they are same, they are kept same. Then I take second pattern, I apply all those learning rules, and then I obtain delta w2. I keep on doing like this, and suppose I apply the last pattern xn, it give me another change in weight, say wm. Now once I finish all these sets, say all these training samples from x1 to xn, then I add all this. So resultant of this is called as then change in weight. So addition of all these weight changes, if I do, and then I do the final updation, then such kind of training is called as batch training. So you can see here change in weight is equal to summation, say pattern P equal to small p equal to 1 to capital P, and the corresponding change in weight for each pattern. So these things are added together. However, the randomness in training samples is found to be more helpful. So this will create a problem that it will remove the randomness in presentation, and the stochastic thing is then lost, and that may create you can say problems that you will not be able to learn properly. So the randomness is important while learning. So what is problem of batch training is it is removing that required randomness in training. Now needs to remember the change in weight matrix separately. This is another issue, memory issue, that this change in weights individuals needed to be kept in a separate space. So this will require a separate space to remember all these change in weights. So you can keep on adding, say immediately. So I have calculated suppose W1, delta W1, then immediately for next step I can add this. I can remember sum of this. So you can solve this problem, but still you will require to remember at least one big matrix to remember all this change in weights. Then you can keep on adding. So when these circuits are very big, so this becomes an issue. Right now, since we have a lot of memory, so this point may not be that significant right now. Now, learning constant can be kept small to get performance close to incremental learning. So this is another solution for batch training, that you can keep your C small so that your effect of randomness will exist. Now this is a solution to this. So we want, say, benefit of incremental learning so that randomness is maintained, and we want the advantage of batch training, that you need not require to update for each and every training pattern. So what is disadvantage of batch? What is, say, advantage of batch? That change in weight happens after a complete batch of training. Okay, so we need not change weights every time. So what is done here, we are mixing these two methods, incremental learning and batch learning. So we take this, say, data set, rather training data set, and we divide into some sections. Say this is section 1, then section 2, section 3 and 4. So these are now called as mini batches. If it was a batch training, we will start with this, suppose, first sample x1, then keep on applying one by one all other remaining patterns till xn. So after presenting all this, for every pattern we calculate delta W. We can keep on adding simultaneously, and then here, once everything is over, we do actual change in weight. Okay, so this is batch training. Now here, instead of that, since I want randomness, what I do, I take this pattern 1, I go up to, say, xk, and here this batch ends. So I will do final, say, change in weight here itself. So one time here, second time here, third time here, and fourth time here. So 4 times I will do it. Instead of only one time, I will do it for 4 times. So that is called as mini batch. So it may be noted that randomness is key in learning. It is advised to use incremental learning and use random selection of training samples for each iteration. In case of deep networks, mini batch is more suitable. So this is a practically observed thing. For deep networks, go for a mini batch training. Okay. Now next point is the steepness of the activation function. So the activation function, suppose I take this bipolar sigmoidal activation function, the equation is 1 minus e to the power minus lambda net divided by 1 plus e to the power minus lambda net. Okay, so if I find out f dash of this, so this function is a of this function f is depending on two variables, say net value of the neuron and the steepness of the function. So if I play with this lambda, you can see, say this is for some lambda 1, and if I make this lambda 1 small, then I may go like this. If I increase, I may go like this. Okay, very similar to the thresholding function. Okay, so we want to see what is effect of such steepness function on my learning. So what I do, I calculate f dash, then this will be 2 into lambda into e to the power minus lambda net divided by this thing. So this lambda is getting multiplied here. Okay, lambda is getting multiplied here to in the equation of f dash. Now you know that what is change in weight. So change in weight is learning constant d minus o into f dash into input. Okay, for output layer. For hidden layers, it is a small change, learning constant into f dash again into this group, that is delta signal into input. So this is for hidden and this is for output. Now when you substitute this f dash here and here, this 2 into lambda will come into picture, which is nothing but a multiplying number. Lambda is sometimes it is 0.1, sometimes I may take 1, I may take 2. So this is just a number getting multiplied to the learning constant. So if I combine this, say c is equal to 2 into lambda into this learning constant, and I call this c as now learning constant. So there is no harm in saying that this lambda plays a role of learning constant, okay, similar to learning constant. So what we do, what we suggest is you keep this lambda equal to 1 in general, don't play with this number, okay, so that this equation will be e to the power minus net divided by 1 plus e to the power minus net whole square. Okay, so this equation will be like this, and activation function is e to the power minus net divided by 1 plus e to the power minus net. Okay, instead of using these generalized equations, we recommend to use these two. That is, you keep lambda equal to 1. You may take lambda equal to 2. What will happen? Steepness will change, but actually it is similar to changing learning constant. So what we do, instead of playing with two numbers, the solution is keep lambda equal to 1, use these two equations, and then you take, as per your requirement, this learning constant c or this learning constant eta. You play with eta and fix lambda equal to 1. So that is a practical approach. You can see here, if I change lambda from 0.5 to 3, then if I change the net at this position, you can see here it is just increasing f dash. So there is a direct relation between f dash and lambda. For net equal to 0, f dash is maximum. So lambda has a multiplying effect. Suggestion is that keep lambda equal to 1 and control learning parameter or constant. Now let us talk about learning constant itself. A lot of things are depending on learning constant. There is no unique value. So keep this thing in mind. There is no unique value of learning constant. Okay, you have to search this learning constant for your problem on your own. Nobody can tell you what should be this. So it is your practice that will make you perfect. A small value for broad minima yields slow convergence. It means that if your error surface is very broad like this, okay, and if you start randomly, suppose from this point, this is your error, and this is say weight. So from here, you have a small, say, learning constant, then you will take small steps, very small steps, and it will take a lot of time to reach to this point. Okay, so what you do in such situation, you can take a big step. That means the learning constant is bigger one, so you can reach the destination in a few steps. So a small value of learning constant in broad minima yields slow convergence. Whereas when you take a large value for a steep and narrow minima results into overshooting. So here is another problem. Say this is my error surface. And if I take the big step, big learning constant, suppose I am standing here for this random assumption, then I may jump this side directly. I am not reaching here because my step is big. I will jump here, then I will jump here, maybe I jump here. Okay, something like this may happen, and you may go back sometimes. So this will happen if you take big step. So this is also not good. So you have to have a moderate step size, not very small, not very big. So learning should be sufficiently small and should be chosen experimentally for given problem. So no, I said nobody can tell you what should be learning constant. But in general, we can choose this as maybe 0.1, maybe 0.01, maybe 0.02. So we can start with such numbers and see the effect, what is happening, and then fine tune. So fine tune is must. So there is something called as momentum method when you are trapped in such flat error surfaces. So we have a momentum method which is a modified version of earlier back propagation. So this is a proposed to accelerate training and reach the convergence fast. So very helpful on flat and non-circular error surfaces. So we will see the example. The, the current weight change is added with a small component from earlier change in weight. Okay, so current change in weight, say delta Wt, is equal to negative gradient of current error plus, and this is a new term alpha, again a constant, a small number in the range, say 0 to 1, not but 0, otherwise this will be not in picture. So if you want to use momentum, so keep this value alpha greater than 0. And earlier change in weight, the previous step change in weight, a small portion of that is added to current change in weight. So this is the method called as momentum. So for total n steps, the current change in weight is given by this formula. So in terms of change in weight, T minus t minus n. So this is the gradient for t minus nth step. So how it is done? Suppose I say change in weight for tth time is equal to negative gradient of error for current time plus alpha into delta w, that is change in weight for previous step. So I can write this term like this. So what is this? This is change in error, as a change in error with respect to those weights for t minus 1 time step plus alpha into change in weight for t minus 2, because for t minus 1 step previous change in weight will be t minus 2. Now if I simplify, if I take this alpha inside this bracket, so this will be minus alpha into learning constant into gradient of error for t minus 1 plus alpha square into change in weight t minus 2. Now if I substitute definition of this change in weight again, then it will be gradient of error for t minus 2 time step plus some change in weight for t minus the change in weight for t minus 3 time steps. So if I keep on doing that, I will get this big sum ranging from say 0th step to capital N step, that is equal to minus learning constant summation n equal to 0 to capital N alpha to the power n into gradient of error t minus n. Okay, so same thing we have seen earlier. Now here the suggestion is you keep this momentum term in the range of say 2 to 0.8. Okay, so you choose some parameter. Now here we are demonstrating how it works. Suppose you are standing here currently. A is the point where you are standing, and these are the equi-error contours. Now once you are standing here, your error gradient is saying that go this side. This is the direction of your change in weight at this position, because minima is here, so it is pointing this direction. Now what we do in momentum method, we take the previous step gradient or change in weight, we add to this. Okay, so this is added with change in weight for t minus 1. So this is one vector and this is another vector. So a small portion of this vector, so small, this much suppose portion of this vector is getting added to this change in weight calculated at this position. Okay, so I can suppose this is my point A, I stand here and I got this change in weight, then I have already seen this direction in previous step, so that direction is again added here. So my next position, instead of at this location, I will be standing here. So I'm getting acceleration in this direction. So that's why it is called as momentum. So I got some momentum in certain directions, I will accelerate more. I will take big steps in the direction that I have seen already, and I will reach the destination fast. So that is the idea. Once you take some momentum, you will take you will move to the direction where error is minimum very fast. Now suppose you are standing here, you are standing at this point C, then you got this direction for the previous step actually. So from this to this you have moved, and now you are suppose here. So when you stand here, you get this direction. Okay. When you stand here, you calculate change in weight, you got this direction. So you will jump here suppose. But in previous step, you got actually this direction. In previous step, you got this direction. Now you are being told that go this side. So you came like this, and now calculation is saying you go this side. Okay. So if it was a normal routine, then you could have gone this side. Then you take say this path, and then you may reach this. Okay. But when you add the momentum term, so this vector, and this was the earlier calculation, and this is the current calculation. So if I add this vector component in this new calculation, suppose I add, so I take this small vector here, and if I add like this, then I get resultant direction as this one. So this is the new direction due to momentum component. Okay, so I reach now directly to this point. Earlier you could have, if you are not using this momentum term, you could have taken this zigzag path and reach the minima. Sometimes you may go ahead instead of minima, and then you may come back. So it will take a lot of time, particularly when your contours are not circular. If contours are circular, then this problem may not exist. But when the contours of error are not circular, they are some elliptical kind of things, then you will face such a zigzag path, okay, for the training. Now this momentum method will avoid this. Okay, so basically the modified backpropagation uses this. So we'll stop here. There are few points: how to choose the network size, how many layers, and so on, so that we will see in next class.